The concept of time is crucial in describing our environment. The passage of time enables us to quantify object change and mobility. At first glance, one could think that with a single clock for the entire universe, time is absolute. Time isn't as simple as we might believe. We tend to work by the clock, arriving at 9 a.m. and leaving at 5 p.m., and our perception of time does not vary during that time, though it seems to slow down before the weekend. At the turn of the 20th century, a discovery radically shattered our previous understanding of relativity. Time is no longer absolute, but relative. Each item has its own time and clock, and two previously synchronized clocks on different trajectories across space can meet again and show different times. What is time dilation? Time dilation is the seemingly strange phenomenon of time passing slower for an observer who is moving relative to another observer, depending on their relative motion or positions in a gravitational field. This is how it works. Time is a relative concept. That, as absurd as it sounds, is a result of Einstein's theory of relativity. We're used to speed being relative in everyday life. For example, a car traveling at 60 mph or 97 kilometers an hour, relative to a stationary observer, would be observed as moving at 120 miles per hour, that's 193 kilometers per hour, by a motorist heading in the opposite direction at the same speed. This same phenomenon also affects time. Depending on an observer's relative speed or position within a gravitational field, time passes at a different rate for that observer than for another observer. This effect, known as time dilation, is only noticeable under certain circumstances, although we are constantly subjected to it at a low level. Time dilation is a consequence of Einstein's relativity, in which time is not as absolute as it may appear. The rate at which it passes varies for observers in different frames of reference. Einstein's starting point was that light has the same measured speed irrespective of the observer's motion. This seemingly innocent assumption leads to the inevitable conclusion that moving clocks run slowly. This phrase is frequently used to describe time dilation, but it's a little deceptive, since it places too much emphasis on clocks, which are only relevant in the sense that we use them to measure time. However, rather than seeing time dilation as a clock property, we should consider it an unexpected reality about space and time. The theory of relativity is divided into special relativity and general relativity, and time dilation features in both. The principle that the speed of light is the same for all observers is crucial in special relativity. According to Boston University physicist Andrew Duffy, one of its consequences is that two observers, moving at constant speed relative to each other, measure different times between the same events. However, the effect is only detectable at speeds approaching the speed of light. 10 years after he proposed special relativity, Einstein expanded his theory to include gravitational effects in general relativity. However, time dilation in this hypothesis is determined by the strength of the local gravitational field rather than the speed of travel. We currently live in a modest gravitational field on the Earth's surface. Therefore, we're already experiencing time dilation without even realizing it. Additionally, the strength of the effect changes when we move up and down within Earth's field. Gravity is weaker on the top floor of a tall building than on the ground floor. Therefore, the time dilation effect is similarly weaker higher up. The further you are from the Earth's surface, the faster time passes. Although the effect is too small to perceive with human senses, the time difference between different altitudes can be measured using extremely accurate clocks. A spectacular example of gravitational time dilation is the region around a black hole, which has stronger gravity than Earth. NASA has considered what would happen if a clock was placed 10 kilometers from a black hole with the mass of the Sun. The clock would take roughly an hour and 10 minutes to show a difference of 1 hour when viewed through a telescope from a safe distance. One of the most perplexing consequences of time dilation is the twin paradox. In this hypothetical experiment of twins, one identical twin lives on Earth, while the other twin travels to a faraway star at speeds approaching the speed of light. When they reunite later, the traveling twin has aged significantly less than the one who stayed on Earth, thanks to special relativistic time dilation. The seeming paradox arises from the erroneous belief that the situation is symmetrical. In other words, you could say that the traveling twin is stationary relative to the Earthbound twin, implying that the Earthling would have aged less than the traveling twin. However, this isn't the case because the situation isn't symmetrical. When special relativity talks about relative motion, it means motion in a straight line at a constant speed. That is not the case in this illustration. Because the twins are together at the beginning and end of the journey, the traveling twin must accelerate from a standstill to top speed, then turn around and head back in the opposite direction before finally decelerating to a stop. These phases of acceleration and deceleration introduce general relativity because they have effects similar to those of a gravitational field. When the math is done to account for this acceleration, it turns out that, like time travel, the spacefaring twin does age more slowly than the Earthbound twin. If you like this video, please consider subscribing and click the notification bell so you do not miss any upcoming videos.